Hello, everyone. I'm Tianjun Zhang from UC Berkeley, and today I'm happy to present our work, Gorilla, connecting LLMs with massive APIs. This is a joint work with Shishir, Xing, and also Joey, who is my advisor. And here's a QR code you can scan, and please, you're very welcome to join us. So let me actually first describe a little bit of the current status of the LLMs. The current situation of the LLMs as a chatbot, they have great capability, but which means you as a user would sit between the LLMs and the actual world. So the typical workflow is we write a prompt for the language models, and the language model would give us a response. Right. After the response, I need to process the response, figure out which other command I should run in the real world, and then I go act in the real world. And the real world will give me a response. Let's take an example first. Imagine I want to order some of the takeout food from either Uber Eats or DoorDash. And then I go ask the language model, oh, it's Uber Eats or DoorDash providing an API that can allow me to order DoorDash or order food from a specific, let's say, Chinese restaurant. And the language model could respond a single command for me. The command would including all of my constraints, like some Chinese food, and the restaurant is still open at this point. Also, it will be having my location, like it's near Berkeley. So as a user, I go copy paste this piece of the API calls, and then I go execute this in the real world. And after a while, the real world give me the response. Like I got my food at Berkeley. But in our point of view, this human sitting in the middle is slightly additional. So what could be the next step for the LLMs, right? It is the LLMs directly interact with the world, which means you as a user would sit at the very left of this workflow. You could let LLMs talk in the middle between you and also the world. So which means LLMs can directly introduce effects in the world. I see in this ideal case, the user would write a prompt to the LLMs, and the LLMs could take the prompt directly, do a little bit of the planning. Right? For example, if I want to complete a workflow, let's see, I want to order a DoorDash food, and I want the driver to pick up my food, come to my home, and but also pick up some of my laundries, sending out into the laundry rooms, and then pick up for me. This is a pretty complex workflow. Then the LLMs would need to figure out what's the necessary steps for accomplishing this. Maybe first we'll call API for a driver to actually pick up my food, and then they call the API to adding additional tasks to the driver. Say, I would like you to also pick up some laundries from my home. And lastly, it will be asking the driver to sending my laundry to a specific location I have decided. So then after the planning step, the LLMs figure out the necessary tools for each step, and then go execute directly in the real world. So after the real world giving some response, which means like it actually sends the driver to me, to the LLMs, to me, and also I could respond to success to the LLMs. Then the LLMs is like sending maybe a confirmation email to me or saying your order has been placed, your food has been ready, and also your task of picking up the laundry from your place is also being solved. So let's take another example, look, specifically tailored to the Gorilla model we trained, which is providing service for the cloud providers and also the Kubernetes calls. Let's say I want A100 GPUs, but I want it in the east of the US. Now, the current language model cannot effectively do this, but let's swap in the Gorilla model. What the Gorilla model would do is first figuring out which of the cloud provider it needs to use. Let's say here we use the Azure from Microsoft. And then the Azure is actually picked from all of our available services. The gorilla would go and pick up the correct service for you from this API pool, and then go directly execute this. And then let's see one of the example on how this can be done. So this is the example, and this is software we created, and it's like a pip install package. You could just simply do pip install gorilla -CLI, and this command will be, this tool will be easily available for you. But let's take a look first at what this model can do. So at first, I want to figure out how to list all my GCP instances. I could directly say Gorilla, which is calling our backend server, and my request is list all my GCP instances. And see, now we see the Gorilla is loading. And here we choose to return to the user 3 different commands, because we're not totally sure if we only provide the top 1 results, the user will be happy, but then we instead choose to provide 3 different results and ask the user to choose which one they would want to execute. So let's see now here, I want to choose the second one. Now the Gorilla directly executes the command for you, and it directly returns you the results. So you don't have to actually go to the website and typing this command, or go open another terminal, typing this command, and figure out these things for you. This is a very good direct demonstration of how human can be sitting aside and let LLMs talking to the world. So now we can see the results here is, Yeah, so now we see the results here. We returns a couple of GCP instances, which include the Poet, Gorilla, and also my GPUs for the undergrads at Berkeley. Now let's take another example. This is example actually, I assume most of us know, because it's just simply RS. But let's see how the language model, how the language model is responding at this case. Now the language model can provide different options. Some of them are wrong, but some of them are equally correct, which is this RS star and then RS-AL. Now, assuming I want very detailed information from all the files, including like the creation time, last modified time, and also different user access, I would choose the number 3 one. And see here, all of the comments, all of the files are listed with their corresponding, with their corresponding name, with their corresponding informations. So this is a tool we have built, and you just need to do pip install gorilla-CLI, and you can use it. It's completely free. We serve this on our backend. And here's the QR code. So for this, I want to actually talk. Now we have actually seen how the Gorilla as a software works. Now I want to talk about how we train this Gorilla. And there are 2 concepts I want to bring up as they are pretty important for the paper. One is called retriever-aware training, and the second one is how we can actually measure hallucination of GPT-4 in this specific setting. I think in general, measuring hallucination for GPT-4 or for any language model is very hard. But for this specific setting, we can provide a way to actually measure the hallucination. I'll be getting to talk about that later. And let's actually start with this first big question: how to mix fine-tuning and retriever. So people have been debating a lot on the fine-tuning versus retriever augmented generation. Fine-tuning means I can take a piece of information possibly from not from the pre-training dataset, because GPT, pre-trained language model or GPT would already have information for that, but for some of the specific use case. Let's say you have some personal data or the enterprise private data. And then I could fine-tune, create question answer pairs to my language model and ask it to give its knowledge of my personal information or the company private data. But another way to do this is I don't touch the weights of the language model. I don't train it. I just provide the documentation as a prompt. And the language model could read the documentation and generating corresponding answers to the documentations. And they have both pros and cons. Fine-tuning are known to be more reliable and more accurate, and it can solve a lot more long-tail problems. But it requires you to update the model weights and requires some computing resources to actually get the model training. And you may need to figure out the correct fine-tuning recipe because it may require mixing different domains of data to actually get to the task having a good performance. Retrieval augmentation, on the other hand, they don't touch the model weights. They don't require additional training, but they are sometimes not that extremely reliable. You may get 50 or 60% of the accuracy when using retrieval augmented generation, but for some of the long tail problems, it won't be as good as you fine-tune the model. So here we provide a hypothesis about this too. At least we wish that is true, which means fine-tuning is more about augmenting the behavior of the model. And retriever is actually introducing new knowledge to the model. So we see some early evidence of the gorilla is that fine-tuning is remarkably effective at the behavior and knowledge, which is contradict to some of the hypotheses we have been made before. And this has been tricking us a lot. So we are asking the question: retriever could help grounding, but being wrong and expensive. So what about we take both sides? So we do retriever and also do fine tuning, and we call this RAT, which is retriever aware training. Let me explain a little bit of the big idea of this retriever aware training, which is fine-tune the model to use or ignore the retrieved text. The model could say, here the text, some of the parts are irrelevant to my question, or if I'm providing the top K results from the retriever, and only one of them is correct. So a model could say, here different documents are actually not relevant to the question I'm asking. So I could choose to ignore them, but only use the ones that are relevant to our questions. So this has some of the effects, which is introduce the correct and incorrect results during instruction fine-tuning. And the second is ensure the model is robust to the low quality retrieval. So this we have been tested a little bit on our model as well, because the model would actually ignore the retrieved context if they're wrong, or if they're completely irrelevant to your question. So here is how the RAT is actually working. So we don't want to do fine-tuning because the fine-tuning would simply just teach the model to remember all of the information from your personal data or from your company's enterprise private data. But instead, we also don't want to do RAG as well, because in some of the cases, we are not super reliable. So we choose to combine them. We choose to combine them together. And how to combine them? Let me give you one of very concrete examples. So here we are introducing this retrieval-aware training, which is the user saying, I'm an engineer at Uber and I need to find an API that can classify the pedestrians. So please write me a Python code in 1 or 2 lines to make an API call in Torshab. We're not only actually just providing the language model with this prompt, we also provide reference context here. So domain is, we have to do is object detection, and we have the framework of function, framework of PyTorch, and function is traffic object detection. So, and it has also corresponding API calls and arguments. Now the assistant, which we are fine-tuned for, have to actually read the corresponding RAG context or the API calls, and then figure out how to actually use APIs to achieve my task. Yeah, and we actually want the model to have this behavior of first determining to use or discard the retrieved API. That's basically saying, I want to ask the question, is this relevant to my question? To the model. And model could say yes or no. If yes, then the model could be responding correctly to my answers, to my questions. But if that's the context is not super relevant to my question, the model would refuse to answer or answer something completely according to its own knowledge. And the step 2 is you can respond to your prompt. So let's say here's a different example, which is the APIs and the model is, and the user question is not it's not relevant. Let's say I'm a Uber engineer at Uber and I need to find an API call to classify pedestrians. But the reference API, like it says semantic examination. It provides me information of doing semantic examination and using PyTorch, and the functionality is neural machine translation, let's say. So this is a completely wrong API and it's not irrelevant to our task. So what the model would do? The model would do is to learn to ignore these APIs and then still up to using its own internal knowledge to actually answer a question in a correct way. This case is extremely useful when your retriever is not good, which we know has to be a very, very huge problem for the information retrieval community. Like if I only ask these questions, not some keywords matching search can help, but then I need to train a specific retriever that is known to be not very good quality when you are retrieving the top 1 or top 5 results. It has to be top 100 results, then the answer could be potentially, you have the recall to be very high. But then there's a question of the language model can be easily distracted by your irrelevant text. So what we are presenting here, the retrieval-aware training, can potentially solve this problem by training the model to ignore the irrelevant context and only to use the correct ones. And now let me ask another question to you, which is also very important. So how much does GPT-4 hallucinate? And some of you may have some idea, rough idea of how much it hallucinates. But if I'm asking a specific number, then no one could answer the question because there's no very good way to measure hallucination. You can definitely check for factual, but there's some other difficulties in there. So for the task, we have been measuring the API calls. It's not general coding. So what we can do is we can construct this AST subtree matching method to actually measure the hallucination. Let's see one example here. On the left is what I collected from my database. So basically from the Torch Hub, we collect all of the Torch Hub API calls, all the corresponding models. And here's one example from the model, which says the API tree is Torch Hub load and has argument of PyTorch vision, DensNet 121, and the pre-trained equals to true. And on the right side is what the model is generated. So the model will generate something like Torch Hub load, PyTorch vision, and then use DensNet 121, sorry. And it also can use other models. For example, model 161, what can have other arguments, which says util is true, and the model zoo is true. And using some model zoos, and has pre-trained equals to true or false. What we have to actually check is what your model writes. Is there a subtree in the right side that contains the left side? This is our question. And if yes, so we find this match. We know that the model is actually calling the Torch Hub API with the argument of DensNet 121 and PyTorch vision, with the arguments of pre-trained equals to true. So now in this case, we know that the model is not hallucinating because the model's call is actually backed up by one of the API calls in our dataset. But if I don't have a match, then the model's calling a function or API call that doesn't exist at all at my database. So we know that the model is hallucinating. And why we choose the AST tree instead of the string matching is because this tree structure is actually more tolerable for different various of additional arguments. Like in Python, we have the default arguments, we have the argument with the default values, and also we are having the arguments like, say, you have the argument name and the actual value with the equal inside, but we can also just specify the value without actually calling the argument name. So using the AST tree makes the evaluation method more tolerable to these minor changes than exact string matching. And here, after answering these questions, I'm going to present to you how we actually train our model, the self-instruct data construction. So what we have in our dataset is 1,645 API calls, 94 of them from Torch Hub. This is because the Torch Hub is a relatively small one, and we exhaustively included all of the API calls. And 626 from TensorFlow Hub, V2, and this is also exhaustive, and 925 from Hugging Face. So the Hugging Face contains a lot of models and API calls. We select top 20 in each domain. And here's our format of collecting those data. Basically, we have each of the API call would have a domain name, which is object detection, for example, in this case. Framework is PyTorch. Functionality is traffic object detection, driver area segmentation, etc. And then we have the API name called hybrid nets. API call is Torch Hub load. Repo name equals to hybrid nets, and model equals to hybrid nets. Pre-trained equals to true. And we specify all the arguments, Python environment requirements, and if this API documentation has some example code, we would include them as well. And lastly, we would include the performance of this model or any metadata. And then there's a description about this model. Like HybridNet is end-to-end perception framework for multitask. Our work focused on traffic object detection, etc. So this is the structure or the framework of our API documentation. So now, given this API documentation, we use a self-instruct technique to prompt GPT-4 to generate instruction and API pairs. This step can also be replaced by manually collecting them, but we just choose easier and simpler way to call GPT-4 to generate. And now the GPT-4 or the self-instruct framework would come up with a question. I'm an engineer at self-driving car company, and I want to find an API that can classify cars, pedestrians from image of the same. So this is the question I will be answering. And the API call would be the previous ones doing the object detection. So the model would want to read from this documentation and write the specific API calls. And then we use this data to train a gorilla, which is at that time a LLaMA-based, LLaMA-7B as a base model, and then use the dataset we construct to fine-tune this model for API construction tasks. And afterwards, we have seen at evaluation time, we have two mechanisms for evaluating this. So once we have API dataset and the evaluation time, if the user asks, I want to see some dancing cats, see some cats dancing in celebration. And for this one way called the information retriever combined in the loop, we would first ask the information retriever to look at our API dataset, which we construct previously, and then give us the top candidates on which of the APIs you think would be most relevant to my task here. And afterwards, I would say pass this both the question and also the relevant text to Gorilla. And now the Gorilla would generate a valid API call saying stable diffusion pipeline from pre-trained from stability and also stable diffusion 2.1. And we can see the execution result. It's like dancing cats right now. And on the other hand, we also provide a zero-shot version, which is due to the retrieving, the off-the-shelf retriever is not that well, performance is not that great unless you do recall at 100, which is limited by the context length of our language model. So now we also provide a zero-shot version, where it says user directly says, I want to see some cats dancing in celebration. And I don't need any context here because my model is already fine-tuned on our dataset. And then we have seen like the zero-shot version, the model would directly generate API calls and execution results. So now we present you the two ways of potentially constructing and fine-tuning a LLaMA-based model to write API calls. One way is zero-shot, one way is the retriever aware training. They both have a little bit pros and cons. The pros of the retriever aware training is, slides I'm going to present next, which is it can adapt to any of the API database change. Like, let's say if I update my API in some ways, the model will be having the necessary information to write the new API calls instead of the old one, maybe the stable diffusion 3.1, etc. But the bottleneck, the cons here is the bottleneck is the information retriever. The information retriever is usually not that good at retrieving the correct API database, especially if the user's question contains a lot of constraints. Let's say I want a model that is accuracy on the ImageNet is larger than or greater than 70%. Then the information retriever would having a very hard time retrieve whether it is resident 101 or whether it's resident 50 or with smaller resident. The zero-shot version, on the other hand, don't have this bottleneck, but it will be less But whenever you want to update your API calls, you want to have new API calls, then you need to fine tune the model again, which is also not great. And so here's like we discussed the pros and cons for our model. And let's actually take a look at how the comparisons of the model generated APIs are doing. So here's the GPT-4 results, right? It generates some ASR model, which is touch upload, but it is hallucinate because it has the source equals to local, which assumes you have a local file in this in your laptop. But I may or may not have a local file in this laptop. Let's see about Cloud. Cloud actually choose the wrong library or the API to process my question. Now it is Gorilla. Gorilla actually chooses the correct API, and also it doesn't hallucinate, which means like this API can be executed perfectly and very reliably. But many of you also know that if I'm showing this example, you'll be questioning, oh, is there a valid test set? Like, can I get some numbers? So on the next slide, I'll be showing some numbers to you, actually. Here's the zero-shot results. More interestingly, we can see that Gorilla can surpass the GPT 3.5 and GPT-4, even the current SOTA model by a lot of the margin. This is actually understandable because GPT 3.5 and GPT-4 don't have that much of the context, which a lot of the GitHub, for example, GitHub or the Hugging Face models are updated after the training of GPT-4 is finished. So they won't have access to those models and cannot generate them correctly. But on the other hand, Gorilla is fine-tuned on those data sets. So it has the knowledge and can actually do pretty well in the zero-shot setting. But more interestingly, let's take a look at the retriever setting. On the retriever settings, Gorilla is at best as GPT 3.5. We can see in the middle is the GPT retriever, which is simply taking the embedding of the GPT model and then do the cosine symmetry match between the questions and various of documentations. We see that this in the middle GPT retriever is actually worse. The performance is worse than zero-shot one, which is actually understandable because your retriever is actually a bottleneck. We often the time see the retriever is retrieving the wrong results. Let's see if I want to do object detection, I want to detect the pedestrians and the cars on the street, but my retriever is returning to me translation API. And now the model gets confused and it doesn't know how to proceed with this API and these questions. So this would causing some of the performance gap between the zero-shot and GPT retriever. On the right-hand side, we see is like the article retriever, which we cannot get access to in reality. But we just want to see with article retriever what's the performance of different models. By article retriever, we mean that the retriever always know the correct documentation to retrieve according to the questions. So we can actually see that with article retriever, the model is getting better performance even than zero-shot. Previously, we have been looking at the y-axis of the accuracy, and note that the x-axis is also pretty interesting, which means how many times, since we can do ASC tree matching in our evaluation metric, we can actually check how many times the model is doing hallucination, which means creating an API that doesn't exist in our dataset, versus how many times the model is just simply choosing the wrong API. From the first step, we see that Gorilla zero-shot fine-tuned version is actually having very little hallucinations compared to GPT-4, GPT 3.5, and Cloud. And both of the models are pretty good when they are providing the relevant context, which means they don't hallucinate when the context is provided. Like this GPT 3.5, GPT-4, and cloud models. Some of you may be asking why the performance of GPT 3.5 is slightly better than GPT-4. We have some hypotheses, but these models are kind of black box and updated every day. So when the time we were testing this, we used the GPT 0314 version to reproduce the results. And we somehow find that GPT 3.5 is slightly better at following instructions than GPT-4. So now let's see a little bit of example on why this is actually the benefit I mentioned before about the retrieval-aware training, which means at test time, I have some document changes. How could Gorilla adapt to test time document change? Let's see, first one is what I'm trained my Gorilla on is we have less than 50, FCN less than 50. And in the next page, what I'm updating is like API v1 versus API v2. I'm updating less than 50 to less than 1.1, which means I may need a slightly more accurate model than the previous version. We see that by providing the context here, so the user is first asking, I want to automatically remove background from the input image, and I have the retrieval results. First is less than 50, and second is less than 1.1. So the Gorilla model's outputs actually automatically update their outputs with the updates of the different versions of APIs. And let's see, that's the second case. I want to actually update my API REPL A to API REPL B. So in this case, I want to change from Python revision to a NVIDIA deep learning examples. And with a similar recipe, I also provide the retrieved results changed from less than 50 to NVIDIA deep learning examples. We can see also that Gorilla is being able to effectively effectively generate corresponding API calls with the updated information. So notice that this is some of the studies we have been able to manually observe, but we don't have a lot of the thorough test yet. We're still working on that actually. And another finding from us is that this test time adaptation, to some extent, the model could follow. For example, the small changes of API versions and REPL names. But if you want to change documents completely, then the model would having slightly trouble following your documentations. And lastly, I want to actually talk about how some of the Gorilla has been covered by the news and also some of the impact we're making. So on the left side, we have the Hacker News, which we have been on the Hacker News top one or top two twice. One is when we released the first paper, and another one is we released the Gorilla Sierra interface. On the left of the bottom line is how our GitHub starts. And please, we have open sourced everything. This is purely Apache 2.0, and we released our dataset, we released our evaluation script, we released our training pipeline. So please feel free to use it and give us some stars if you like it. On the middle line is we are covered actually by a lot of the media. We have been covered by the Daily California, which is US media. We're also covered by a lot of the Chinese media like Jiqi Zhixing and some other WeChat official accounts. So on the right side, we're having actually self-hosted model for running at our own servers and trying to get things working. So we provide a we provide a Colab book for people to try our version of the API calls. We also provide GitHub CLI tool, which is can be easily used via pip installs. And from these tools, we have been combined receiving 300K invocations in the past 2 months, which means like the users are trying this model and really the model is get something working. So here is the last slide I'll be presenting today. And so here's a little bit of conclusion here. Like from the paper, is we use Gorilla how to write accurate APIs. We also create this benchmark evaluation metric using the abstract syntax tree to let us effectively measure how we can effectively measure the hallucination of the language models with the help of our tree matching method. And also, Gorilla is an open source project from UC Berkeley. You could easily contribute to your own APIs. You could train your own Gorilla model with your own data sets. And this is completely commercially free. Please come and join us if you are very interested. And on the bottom line is what our contact. I want to actually deeply thank you for listening here. And please feel free to reach out if you have any additional questions.